Okay, it's not practical. Okay, it's not practical to build up the accumulator because the slab is infinite. Okay, so therefore we use low theta form. Okay, we use low theta form. If you remember when we define how to identify the orientation, right? How to identify the orientation of an object. We mentioned that before, okay? But let's take a look one more time, okay? So we use a low theta form, okay? So here's the line equation. Actually, we already talked about this before, okay? So, but let me just write it down. It's xi times cosine theta plus y times sine theta should be equal to low. Okay? Theta is the angle, okay, of the foot, right? This is the foot. Okay? The angle between the foot and the x-axis, and low is the distance from the foot. Okay, that's it. It's much easier. Okay, they are exactly the same, but with different expression form. Because this is not good, right? This equation is not good enough. Okay, so we convert it into this form. Again, here is xi and yi. Xi, yi, again, there must be an H point. Now, our accumulator now becomes theta and rho, or rho theta, that'll be fine, okay? Either way, okay? This is much better. And this is how we implement with the Hall transform for line detection. Now, for this equation here, you don't need to calculate the distance of the foot. The only thing you need to try out is what? Is the theta. Now the question is, what is the range of theta?
-1 to 1.
Okay, if you use a pi, then it's between positive and negative pi. Or if you use degree, it's only between what? -0 and 180 degrees, let's say. And most of the time, we use a resolution of 1 degree. So it's very easy to control. Okay, the theta here, okay, you can think of that as about 0 degree and 180 degree, let's say, okay? Or positive, negative 90 degree, they're the same. Or between 0 and pi. But most of the case, we use degree. It's much easier because it's quite easier to digitize the accumulator, okay? And rho, you can convert, in a digital image rho, you can specify with a pixel, right? A pixel, that's not simple pixel, the distance in terms of the pixel. So this is much easier to control. Okay, so we don't use slab intercept form, instead of we use low theta form, because theta, the range is quite limited, it's so small, right? With a resolution of 1, then you need only try out 180 degree difference. 0, 1, 2, 3, and up to 180. And once you have the H point, SI, YI, then we can calculate corresponding foot distance rho, and then we can accumulate, right? Then we can accumulate the volt plus 1. That's it, okay? So this is the equation we use for line detection, okay? As I mentioned, no matter the line is occluded or the image is quite noisy, it doesn't matter. The only effect is on the accumulated value, okay? That's it, okay? So very effective, okay? And very fast, right? First, you apply the gradient or edge detection, and for every edge point, you try out, each point you only need to try out 180 combination. And then you use this equation to calculate rho, and then you do the accumulation. And then finally, you identify the peak, okay? That's it, okay? That's all you need to do. Okay, so here's the pseudocode for the voting. Okay, then for X, for Y, for OX, for Y, if XY is the edge point, then we try out, as I mentioned here, we're starting 0 degree up to 180 degree with a resolution of 1 degree. And we calculate rho, and then we do the voting, okay? And at the end, here's a recommendation, okay? I'm not quite sure about OpenCV will provide this further processing or not. Because as I mentioned, if you have an image like this, okay? Now, all the edge point, as I mentioned, if you put those theta, you can see that if they have 100 point, you will see a 100 line intercept at the same point, which is not true. It's not, I mean, not true is they might have an intersection around. They won't intercept exactly at the same location. No, in a digital image it is not possible. But you were around, okay? You were around somewhere. So that's my suggestion. You have a better. Here, you accumulate all the low theta in the neighborhood, okay? In the neighborhood. For example, 3 by 3 neighbor or 5 by 5, it depends on the accuracy of your algorithm, but you will try to find, okay? Then you do the summation and make it as a new accumulated value, okay? Because there's no way all this 100 point, they will intercept exactly at the same location. No. Okay, which you got to believe you might have something or intercept, right? Okay, in the neighborhood. Okay, so you have to better to do this. Okay, before you identify the peak. Okay, identify the peak. That would be bad. Okay. Well, actually, here's something I will further recommend it. Once you have you identify the peak, okay? For the peak, if this is the peak is at low theta, okay? If this is the peak, okay? Then I will suggest you to readjust as well. For O is neighbor, okay? Okay, I have, okay, I'll show you later. I believe you will have equation to readjust, okay? But anyway, the best way just go through the mean square error, okay? That would be better, okay? So here shows you, if we use a slot-intercept form, okay, each line in the parameter space, you will see a lot of lines that will intercept at the same point. But if you go for the low theta form, because low theta form will show you the sine wave, okay, it's a sine wave. You will see a lot of sine wave. When you read a paper or from the textbook, you will see a lot of sine wave. But anyway, all the sine wave will intercept at the same point here. Then again, this is the peak, okay? I'll show you the evidence of an H in the image, okay? So this is the slot intercept form because it's another line in the parameter space. But with the low theta form, this form actually is a sine wave. But anyway, the idea is the same. We try to identify the peak or the voting or the accumulated value. Okay, let's say. Okay? So here's an example. Okay, the first one is the image. Okay, it shows you the highway or freeway length. Okay, you can see a lot of line right here. See that? Right? And the image in the middle is the edge image or gradient image. Okay, it looks so good. You might carry out with Canning edge detection. You can see some of the line are missing, right? Or they are broken. Okay, but it doesn't matter. And this is the result from the Hopf transform. Okay, you can see from here. You can see there's more than one line. Okay, so again, you might apply what? Maximum, non-maximum suppression. Remember when we talk about the corner detection? You just retain the local maximum or you try to find the mean, okay? Because for this case here, you will see a lot of line in the neighborhood. That's true because the line is not only one from here, see that? Actually, you will see there's a two line, right? You have a two line here, okay? But if you won't care only about it, then you will do the non-maximum suppression, which means you just retain the local maximum accumulator, okay? If these two lines are too similar to each other, okay? But anyway, that's the result, okay? For line detection, okay? For line detection, okay? It shows pretty good, okay? But anyway, when you apply that, you need to set up the threshold. Okay? Again, you need to set up the threshold. Now, next, circle detection. It does not have to be a full circle. It can be any circular arc. Okay? As I mentioned, you can identify a full circle, but if the circle has been occluded, it'll be fine. Even you have something like this, it'll be fine. Okay? You just reduce the peak. Okay? Or even it's broken, it doesn't matter. Okay? It doesn't matter. So you can identify a full circle or a circular arc. Okay? That'll be fine. Now, here, as I mentioned, when you apply the Hopf transform, you need to specify the equation with parameters. Okay, for circle, we have a 3 parameter, which is x0, y0. Okay, it is the center of the circle, and r is the radius. Now, you need to try out every possible center, all the possible location. Okay. Even the center may not be within the image. For example, if you have an image like this, and if you have a circular arc like this, which means what? Here's the circle, and the center is right here, which is out of the range of the image. that could possible. Okay, that could possible. If this is something you're looking for, you must be very careful to specify the range. Okay, but especially for industrial application, because you have some good idea about the size of the circular part, right? Which means what? You know something about the radius. You might have some, you don't have any arbitrary circle. So you might only have a small, this with radius R1 and radius R2. Then you just need to try out R1 and R2. You don't need to try any others radius. Okay? But if you have no idea at all, you had better go for this equation. You try out every possible location, but remember the location or the center may be out of the image range. Okay, that's the idea. But again, most of the time we don't use this. We don't use this equation. Okay, we use another equation. But that's the idea. Okay, so for this case here, we need a three-dimensional array accumulator that include the coordinate of the center x0, y0, and the possible radius. Okay, and once you find out an edge point that fit this circle, okay, with a parameter x0, y0, and radius, then we accumulate or we vote for one. Okay, that's it. Okay, the idea is exactly the same, just line detection. Okay. So for this case here, you need to try for every possible edge point, okay, and then try out every possible location of the center for all x0, y0, and then we use this equation to calculate the radius. Okay, that's one. Then we accumulate the corresponding array. That's it. Okay, at the end, then you try to find the peak. Okay, find the peak, and that's it. That's for circle detection. So it's much easier. Again, you won't be affected by a random noise or very complicated background. 好，所以它这边也是一样，可是你这边需要一个三维的得加钱 ，OK？ 好，这是在早期为什么会觉得很困难？因为你的 memory， 你要开出的 memory 很困难 ，OK？But for real implementation, we go for the polar coordinate. 我们用极坐标的方式 ，OK？ 我们用极坐标。We use polar coordinate. We don't use the Cartesian coordinate. Okay? So here's the polar coordinate. Okay? This is the first. We assume the center of the circle is at the origin. Okay? With x equal to 0, y equal to 0. Now the polar coordinate, you need to specify the angle. Okay? Between the radius, the current line here. For some point xi, yi, okay, and the angle between this line and the x-axis. Now, for here, the polar coordinate can be calculated. Xi prime becomes r times cosine theta. Y becomes r times sine theta. That's it. Okay, and the good thing again is what? Theta is between not 0 and 180, but 0 and 360. Okay? 0到360度 between, okay? Right? Between 0 and 2 pi. Between 0 and 2 pi. Okay? Not 0 and 100. For 9, the slope, okay, is only between 0 and 180 degrees. But for the circle, see that you might have a opposite point right here, but the angle will be, you need to plus 180, right? You need to plus. If you have a point here, right? Then the opposite point, J, YJ. Okay, if this is theta is 45 degree, then the theta must be 45 degree plus 180 degree because the difference is 180 degree. Okay, so the range, but it's no big deal, right? The theta is quite limited. So you can just try out, if you use 1 degree as the resolution, you need to try out 0, 1, 2, 3, and up to 360. That's it, okay? No big deal, okay? So for implementation, we go for the polar coordinate, okay? We go for the polar, but the center may not be always in the origin, right? So we need to shift, okay? Here's the shift with the polar coordinate, because now the center, we assume the center is the origin. Now we shift it to any location. That's the center, okay? In the original coordinate called x0, y0. Okay, again, they are the center. Now, but it's nothing but just arc sine theta plus x0 and arc sine theta plus y0. That's it. Okay. Here, this is our final equation. Okay. Because for this one, we simply assume, okay, the center is at the origin of the original coordinate. But in reality, the polar coordinate, the center of the polar coordinate can be anywhere in the image. So we simply assume the center is x0, y0. Okay. So again, we can calculate x0, y0, which is the center of the circle, as a function of r times theta. Again, theta is quite limited. Okay? But for the Cartesian coordinate, you need to try out every possible x0, y0. And as I just mentioned, the center could be out of the image, right? But if we go for the polar coordinate, the center is a function of r and theta is the limit between 0 and 360 degrees. That's it, it's calculated. And especially for industrial application, you know something about the radius, then you need just try out some possible radius. You don't need to try out every possible radius. So that calculation could be fast, okay? So the only thing here you need, but you need two loops, okay? Here, for every possible h point, then you need to try out every possible radius r. And for all theta between 0 and 360 degrees, then we calculate the corresponding center. And then we accumulate the corresponding array. That's it, okay? That's it. This is the final implementation, okay? It's still very fast. It's still very fast, okay? Okay? But we need a 3-dimensional array for that, okay? And after that, then we try to identify the peak, okay, from the accumulator. That's it, okay? And again, you can use the mean square error to fine-tune the center and the radius of the circle, okay? 这是做完以后, so at the meantime, when you do the accumulation, you need to recall what are the points that fall on the circle, okay, with this parameter, okay, x0, y0, and the radius r. And after that, after you identify the peak, then you go back to look for the h point, and then you try out the mean square error to fine-tune the parameter value. Okay, so that's it. That's the whole procedure you need to do. Oh, that's what I'm saying here. Okay, well, you can refine. Okay, you can refine. That's for night. This is for night detection. Okay, suppose this for night detection. Okay, then we can readjust the parameter x by given this parameter value x plus I in the neighborhood and use the accumulated value as the weight, right? Then we can use, as I mentioned, at the end you might have some local peak here and here, right? And each one has its own accumulated. Then we use the accumulated value as the weight, right? And the denominator just summation of the accumulated value, right? Then we try the weighted mean of x, okay? Which could mean the slope or theta or rho, or this could be the center, okay, for the circle or the radius for the circle, okay? That's if we don't want to apply the mean square error, okay, this we can fine tune the parameter. As I mentioned, they will intercept exactly at the same location, but it will be around the peak. Then we use the accumulated value as the weight 啊，所以那个值越大的话，我们的权重就越大。那我们重新调整了它的参数值。Right, this is the weighted. Okay, we fine tune the weighted the parameter value based on the accumulated value. See, that is something you can do. Okay, even OpenCV does not provide this. You can write your own code to fine tune, or as I just mentioned, you can go for the mean square error one more time. Okay, and to fine tune the estimate or parameter. Okay. And I also mentioned this before, okay, we try to, before you identify the peak, we will accumulate the voting value in the neighborhood of the peak, okay? That's it, okay? So this is very practical to apply, okay? For the accumulation and for the estimate, the parameter value, by using the accumulated weight, okay? That's it, okay? That's for line and circle detection. And then you can extend it to anything for ellipse, okay? As I say, ellipse might have or hyperbolic, okay? 抛物线、双曲线、什么线 anything that can be expressed by parameter, okay? By parameter, okay? I was, here, show you the example. Okay, that's for circle detection. This is the input image. But anyway, you need to try to find the edges. It looks very complicated, right? But anyway, you can see the pupil here, the circular pupil here, right? But anyway, here's your final detector circle. Okay, it looks pretty good. Okay, even you have a very complicated background. Okay, eyebrow, eyelace, another noise. Okay, you can still identify here because visually you can see. There's a circle here. Here's another circle here. Okay, so it will fit the circle well. Okay, so that's another application. Let me mention one more time. It does not have to be a full circle, okay? It can be a partial circle, even it's occluded or it's broken. It doesn't matter, okay? The only effect is just the final voting value, okay? That's it. I won't say anything here, but the idea is you can identify something for this. For example, if you have something like this, this cannot be expressed by parameter. No, there's no way. Okay, not line, circle, but for this, it identifies the corner first. You identify all the possible corner first, and then because it has no parameter, so it manually or actually it can be anything. It manually give you a so-called a reference point. Let's make it a YC. Okay, you use the reference point as the parameter. So if there's something in the image, okay. For example, we have a two thing here, then you will try to accumulate the reference point. Let's say, okay. So for your after this course, for your research or for your work, if you have anything that can expressed by parameter. If there's no parameter, you can assign your own parameter, and then you can use the idea of Hopf transform for peak detection. Okay, so that's the only idea. Okay, and this is based on the corner point. Okay, you identify the corner point. Then if you want, you can go see the details. Anyway, you will try to find. You use the distance as the feature, okay, and then you try to find some parameter. That's it, okay. Then you do the accumulation. If you want, you can take a look, because nowadays. This is the so-called generalized Hopf transform, called generalized Hopf transform, which means what? It generalize what? It can generalize to identify any object. But nowadays, nobody uses it. Why? Because deep learning can do the job well. We don't need to use it again, okay? But in the early day, the Hopf transform has been extended as a so-called generalized Hopf transform. So any object can be used to identify. Okay, but nowadays, I mean, if we want to go for object detection, we simply use the deep learning approach, which will be the topic. Okay, after we finish the part. But for line or circle detection, Hopf transform is still very useful, because if you go for the deep learning, the training could be almost not possible, because you need to train every possible combination of the line or the circle or partial circle or one. I mean, it could be very difficult. Okay, so if you are interested in how you work, and then you can go through all the details, okay? So I will skip this part, because for object detection, or it's very for object with arbitrary shape, we don't need to use Hopf transform anymore, okay? But anyway, when you go for the line or circle or circular curve detection, Hopf transform definitely is a good approach. Okay. We are almost done. Okay, the last part will be the texture analysis. Okay, but before we end it, I already finished the Hopf transform. Okay, for line and circle detection. With still a little bit of time. Let me say something. About the optical flow, okay, optical flow, because it could be, because in this semester I didn't say anything about motion analysis. When I say motion, you need to do some video analysis. It's a video, okay, it's a video. 我没有谈过, but optical flow could be very important. Even nowadays, people use deep learning for video analysis. Some use optical flow as the input instead of the original video image. Okay, so let me just say something. about the optical flow. Okay, so we still have time. Let me take 10 or 15 minutes to talk about the idea. There's a lot of different versions of optical flow. I just talked about a simple one called Lucas Collant. Okay, simply as LK optical flow. There are a lot of different versions, but this is the most simple one. And actually, this optical flow, this LK optical flow, is originally developed for image registration, not for motion analysis. But people extend it for video or motion analysis. The idea is okay. The idea is like this. I just keep saying, when you develop algorithm, you need to think of what will be the idea. What is the good idea, okay, to handle this task? And then you need to think of how to convert the idea into a mathematical procedure or algorithm. And finally, how to convert the algorithm into a programming code. That's it. Okay, the idea is like this. For some frame, because we are talking about video, okay? And frame t plus 1. It does not have to be 1. It could be t plus 2. Okay. Suppose we have an object like this. Okay? If I have an object like this. And then we move, okay, this object, or I should say shift, to the right, okay? I assume this object will shift to the right. So I use the dot line to represent its previous location, and the red one will be the new location. Okay? Everyone follow me? Now we shift to the right, right? Just shift to the right. Okay? For a very small distance. Now, suppose we have a point here called A. At time t. Now, what would happen for the same point A? At t plus 1. Assume the time difference is so small. Okay? Now, the assumption here is, in a very short period of time, the same point at the current frame and the same point in the next frame, their graph value should be the same. Right? It's a reasonable. It may not be true, but it's a reasonable assumption. Right? 就是说，同样的点 A， 我往右移几个 pixel， 可是呢，在那个很短的时间差里面呢，它的灰阶呢，甚至它的颜色呢，应该不会变。Right? You won't see the change of the intensity, right, in a very short period of time, right? They must be the same. It's based on this assumption, okay? At t and t plus 1. So actually, I can put a t plus delta t. Okay, if I put a delta t, which means in a very short period of time, okay? Shift to the right, okay? From time t to t plus delta t, okay? So if I make it more general form, I can put it like this, okay? T plus delta t. Okay? And they must be the same. So for this case, what would happen? for this image, you will see something. I mean, originally, what you see is like this. Okay, so if I delete all the white line, that's the only thing you can see here. Right? Everyone follow me? You won't see anything else. You won't see anything else. Okay? You know what I'm saying? Yeah. This is the so-called optical flow. OK， 光流是这样定义的，这叫光流。OK， it's optical flow. Under assumption, in a very short period of time, the same point, okay, at the current frame and the next frame, the intensity should be retained. Okay, and the difference, you can call this is the movement, right? This is the movement. For each individual pixel. That's so-called optical flow, okay? So now we can see that optical flow is represented by the local image motion, okay? We by evaluate the local derivative, okay? We evaluate the local difference, okay? In the consecutive image in the video sequence, okay? So that's the optical flow. Now, in the LK method is under the assumption, okay, you may highlight this, okay, the motion constraint equation, okay. The optical flow is based on the motion constraint equation, which means what? Under the constant brightness assumption. Okay, you might highlight this statement here. You will maintain the constant brightness assumption, which is what I'm saying here. This is exactly what I'm saying here. Okay? In a very short period of time, their brightness or intensity will be retained. Okay? It won't be changed. So here comes the equation. Because we are talking about the video is a three-dimensional, SY is a spatial location in the image. T is a time frame T. Okay? Now we shift by delta x, delta y. Okay, x is shifted by dx and dy because it can shift in any direction. For this case, we shift only dx. There's no dy. Okay, and also the time has been changed from t to t plus dt. That's it. Okay, at different time. So everyone can follow me. Okay, it's under this assumption. The graph value will retain the same at frame t and frame t plus dt for a very small time period dt. Okay, then we shift by dx and dy. Okay, so for our case here, we shifted this is dx and there's no dy. Okay, because we shifted horizontally, okay, to the right. Okay, so we have a dx, but we don't have dy for this case here. Okay, so this is the equation we have. Okay, this is a motion constraint equation under the assumption we have a constant brightness or constant intensity. Okay, so the graph value It's the same. Now, again, you use terror expansion. Okay, terror expansion. Remember that when we talk about Harris core detection. 泰勒展开式，再看一次啊 ，terror expansion. For the right hand side, we just do it for the right hand side. Okay, we do it for the right hand side. Remember, we can plus 8, right? And plus first derivative times x minus 8, right? And plus the second derivative and so on and so forth. Right? Okay. For the Lucas optical flow, you use only first order, as I mentioned, in digital image. Everything after the first derivative is not stable. Okay, so you use only the first derivative. So it says the right hand side is x plus dx, y plus dy, and d and t plus dt. Okay, can be write down based on the first order pairs expansion. We can write it as like like this. Okay, we can do something like, because the first derivative, okay, so we take it as the first derivative with respect to x, with respect to y, with respect to time. Okay, that's it. Okay, the first derivative. And the difference, okay, you can write it down as x, y, and t, right? Right, we use this one, right? Just like 8, we put this as 8. This is x. So the difference is not, but the difference here is what? Is x plus the x and minus x. So the result is dx. That's why we put dx here. Everyone follow me? This is the first order. Okay, this is the first order Taylor expansion for the right hand side. Okay, for the right hand side. Okay, everyone know? Okay, and now we can cancel out this term, right? Both are the same. So what is retained is like this. Okay, just like this. This term, and this term should be equal to 0, right? Everyone know what I'm saying, right? 因为这是既然这个 this term is nothing but this term, and the right hand side is replaced with the first order pair expansion, okay? And we can cancel out these two terms. So what is retained is this term. So everything for this equation we divide by dt, okay? By dt. That's what we got. U is specified dx over, well, actually this should be okay, and plus anyway, we take it to the right hand side. Okay, what we got is, that's it. Okay? This turn and this turn is what? In a 1 unit of time, how much we move in the x direction. This is 1 unit of time, how much we move in the y direction. And this is the derivative with respect to time, okay, in the time domain. So actually, dx, dt, and dy over dt is the so-called optical flow. Okay, we use YuanZe to represent the shift in a 1 unit of time. 单位时间，它 x 轴位了多少？单位时间 y 轴位了多少？这个叫 optical flow. Okay, so from here, actually, this is, so for this case, u, but dy over dt is v. In our case here, v equal to 0. We didn't move anything. So optical flow is what? Optical flow is a vector. Optical flow, okay, remember, optical flow is a vector. When I say a vector, I mean what? It shows you each optical flow, each point have its own optical flow. An optical flow is a vector, and a vector contains the length, the distance it moves, and what? And the direction, and the direction. 只要我们谈它是向量，向量有2个东西，第一个它位移多少，它的量；第二个它从哪一个方，它移到哪一个方向。Okay, so optical flow has 2 things. Okay, how much it move. Okay, what is the length it move? What is the direction it move? Okay, that's it. Okay, let's take a break.
最后的那个最后大活做，因为它那个只要3个字的词。你要看吗？你晚上还是什么都方便再睡我吗？